Hello, all. As an embedded and firmware system or systems engineer, when we design and writing and optimizing the programming and firmware, we need to think beyond just writing the functional code. So, we are operating at intersection of hardware constraint and the software reliability. So, there are few critical factors that need to consider and structured across the workflow of an embedded systems engineer. First is hardware architecture and constraints. So, when writing a single line of code, we need to thoroughly understand the target microcontroller or the microprocessor that we're going to work on. So, in that, we need to understand the memory limits. So, we have to first monitor and flash. We have to monitor our flash memory and the SRAM, the data memory. So, and also in this, we have to avoid using dynamic memory allocation, the MLOC and free in deep embedded systems to prevent heap fragmentation. And the second thing is we need to thoroughly read and understand the data sheets and the register map, and we need to put them handy. Because we need to exactly know how the configuration of registers alter the hardware behavior. And the third is the pin multiplexing. So we need to ensure the GPIO configurations that match the hardware schematic, like example, like pulling a particular pin high or low internally, or to setting it to an alternate function like SPI or UART. So I've worked on RP2040 where a single pin can be used as an I2C or else as an SPI pin. So when we are developing a PCB and when we are connecting an IC component to that particular microcontroller, we need to understand and be cautious enough while wiring the IC to the particular GPIO pin. And then the low level communication and the peripherals. So our firmware needs to talk the circuits outside the world reliably. So we need to understand first. We need to understand the protocols. Protocols, as in how the particular device is talking to the microcontroller, which is the brain. So the every protocol is like a language, like how we're going to talk to the particular microcontroller. So we need to choose and configure the right bus for the right job. Like let's say if you are trying to use UART, like simple point to point asynchronous, that requires the baud rate. But yeah, if you are going with a single point to point communication, then try to use UART. And then if you want a two wire master slave and easy to work with, and this is great for the short distance sensor reading, but it's somewhat slower because it works in half duplex. And then if you want high speed data rate, then you can go with the SPI. So because it's a four wire synchronous high speed, and ideal for displays or like flash memory generally. The RP2040 is QSPI, like quadrature serial peripheral interface. So where they have four data lines. Generally SPI has two data lines, right? So it has four data lines. And then for automation and autonomous systems like car, bus, etc., they we use scan the controller area network. So it's a high reliability. It has differential signaling. Because of differential signaling, the noise gets cancelled, and crucial for automotive and the aerospace telemetry generally. And then comes using polling or interrupt. It depends upon the uh, importance of the particular data that needs to be sent to the user, or else like to you have to monitor something. Let's say if the task is simple, just blink an LED, or else like take every sample data of a particular sensor like accelerometer. Only the project contains only the accelerometer. Then it's a simple task. Then you can go for the polling. If you have like n number of sensors, and then you can use interrupts. Like it will talk to the CPU in such a way that now the data is ready. You can get the data and pass it forward. Then the interrupts will be helpful. So Generally, we need to avoid polling in tight while loops because it wastes the CPU cycles, and you can use interrupt service routines for like time critical events. That is what, like keeping the ISR code as short as and as fast as possible. And then then comes the real time execution behavior, like how the things need to be executed. So in this, embedded systems usually have a strict timing constraints. Like it depends upon the domain that you are working or is the use case that you're gonna build this uh, project upon. So in that, we have bare metal, and this is always like that is present, like bare metal versus real-time operating system. Like you can use bare metal, which is a super loop architecture for simpler, low power and deterministic systems. You can use RTOS, that real-time operating system, like FreeRTOS, Zypher, etc. We have a lot of real-time architectures recently coming upon. So yeah, if you need to manage, you can use RTOS if you have to manage multiple complex and concurrent tasks with strict prioritization. And then there comes the other things like timers and watchdogs. So always implement the watchdog timer. It's like a, it just kicks in. Let's say if you put a, if you wrote an algorithm in such a way that for every 10 seconds kick the watchdog. So if the task isn't completed or stuck or hang in between, if the watchdog isn't get kicked enough, so then the whole system will get restart. So, and also like timers, you can use timers in like strict priority based uh, projects where you can, there is requirement of deterministic things that needs to be done in the particular project. And if the code, that is what, like if the code gets stuck in infinite loop or crashes due to an unexpected rate, the watchdog timer safely resets the system. And then signal integrity and the data processing. Signal integrity and data processing. Data coming from the physical world is rarely clean, right? So debouncing, let's say if you press a switch, sometimes it gets bouncing in such a way that uh, digital inputs, like that is what, like buttons or switches mechanical vibrate. So what happens is it takes a false input and executes the thing that is connected when the switch is pressed. So it can cause a huge issue in the real time systems. So we need to use debouncing concepts in such a way that we have to give a time, like if the time for 50 seconds, if you got another switch vibration thing, just do it, or else like it's a false alarm, like that. So digital inputs like buttons and switches, they mechanically vibrate, so we have to implement software debouncing to avoid these false triggers. And then ADC and we have ADC and DAC tag sampling. So we have to ensure the sampling rates satisfy the Nyquist criterion. We have the Nyquist criterion, right? So it's use software filters like moving average or Kalman filters to smooth out the noisy and the sensor data. And concurrency and race conditions. If a variable is shared between in the main loop and an interrupt service routine, declare it as volatile so that the compiler does not optimize it away and protect it using the critical sections or mutex. So this volatile is like a savior, because generally volatile does a great thing that it does not make the compiler to be optimized. Because let's say if you have set a flag, and if compiler get optimized and in the runtime the flag gets changed, the compiler don't, if you don't put it as a volatile, the compiler thinks that doesn't gonna change in the whole code. So this volatile is helpful in the embedded systems a lot. And then power management. Then comes the power management and robustness. So many embedded platforms run on battery power or operate in harsh environments. So we have to use sleep modes so that we can utilize low power or deep sleep rates when the system is idle, and can configure external interrupts to wake the microcontroller. And also we have to focus on error handling and fail safes. Like you have to ask yourself, like what happens if a sensor get disconnected mid operation. Like we have this something called FDIR, right? So failure detection, isolation, and reconstruction. So if the sensor gets disconnected in the mid operation, then the code should gracefully handle the disconnected I2C or SPI lines instead of freezing the entire pipeline. So sometimes if this happens, like the I2C bus gets hanged. So what we can do is we can use bit banging. We can manually take a control of that particular I2C pin to a software input output like SIO pin, make it into SIO and toggle it 9 times in such a way that all the bits, whatever it is, if the get stuck, it get unstuck, and then you can safely use it back to as an I2C pin. And then we have to consider tool chains and the traceability. So we have to master toolchains like STM32 cube ID, ESP IDF, and whatever, like all the Linux OS, everything, hardware abstraction layer or board support package, and just have to move beyond that printf for the debugging as well. Like you can use JTAG or serial while debugger, SWD debuggers to get set breakpoints, inspect the memory registers in real time, and use oscilloscopes instead of just hitting the head around like 2 a.m. Just by debugging it to understand how where the issue is. You can just use an oscilloscope, find the voltage and the current signals where it is getting stuck, like what is the issue. And then or else you can use logic analyzers to verify physical signal timing against your firmware logic.